So here's a quick recap of skills that at some point in your life that are associated with trigonometry that hopefully you remember. So I mentioned a few of them. First one, you should be fairly familiar with c squared equals a squared plus b squared. Pythagoras' theorem. Or Pythagorean theorem. You guys feel pretty comfortable knowing how to use that? Okay, good. Okay. Another skill you should be hopefully familiar with is SOHCAHTOA. The idea of like sine of an angle being equal to the opposite over the hypotenuse. Really going along with that, you should understand triangles. And just the terminology we use. Like for example, this triangle right here is a right angle triangle. And you know that because there's a little box in the corner that indicates a right angle. This side right here would be the hypotenuse, guaranteed. Anybody know why? That's actually a pretty good definition for a junior high student, but that's actually not the better definition. That's the better definition, yeah. It's what's across from the right angle. You probably were told like a half-truth back in junior high that the hypotenuse is the longest side. It is, by the way. Like, I guarantee it, the hypotenuse will be the longest side. But the reason why it's the longest side is because it's across from the 90 degrees. That's actually a better definition. Where would the opposite and the adjacent go in this triangle? It's actually an impossible question to answer because it depends on what angle you're looking for. Clearly, we know this angle right here is 90, so we don't have to look for that angle. So let's say you were looking for this angle right here. Yeah. Now, if you were looking for the other angle, though, it would flip. Hopefully, that's the sort of stuff that you're kind of familiar with. I mean, not that I'm not going to go over it as we go over this big unit of trig, but it definitely helps if you're kind of you've seen it before. Another thing you have to be able to do is work with square roots. It's not actually part of trig that you've learned it before, but if I were to say give you the square root of let's say 49, you guys know that's equal to 7, right? But if I were to give you the square root of 20, do you guys know that that's equal to 2 root 5? I did that in my head. You guys know how I did that, though? Okay, so...
Please excuse the interruption. Grade 7.
20 is 4
and 5. Who need to have retake taken, please go to the meeting room.
4 can square root. 4 squared is 2.
Grade 7,
so
please go to the meeting room for
Does that make sense?
retakes.
The last major skill I can think of is stuff that I would have taught you guys last year, and it involves like making a grid. And we can plot a point on a grid. For example, I could plot a point right here at 6, 7. There was some terminology we would have learned last year, where like this is an arm of a triangle, and then we can make a triangle out of this point by like dropping a line all the way down to here and drawing one across, and you can kind of make a right angle triangle out of this. You guys recall doing this at all? The 6 would be right here, the 7 would be right here, which means that we can find this side, because it's going to be 6 squared plus 7 squared, all square rooted, whatever that number is. So 36 and 49 would add up to give you 85, I guess. So we'd say that that's root 85. And we did some work with just generally the idea of triangles on a grid. Do you guys remember how the grid coordinates work? Like where coordinate system 1? Yeah, this is the first section. That's kind of like the standard position one. And then here's the second one, the third one, and the fourth one. The biggest issue about putting triangles in quadrants 2, 3, and 4 is that now you get some negative numbers. And that helps to explain like why when we eventually, I mean, you guys probably did this a bit last year, but when you like take sines and cosines of different values, sometimes it's negative, sometimes it's positive. It's based on how this angle right here makes something in either this quadrant or this one or this one or this one. Does that ring some bells at least? Okay. Okay. Well, let's start with my new notes then. Before I do, this is actually a really good time of year to talk about where trigonometry fits into everyday life. Some of you guys took physics with me, correct? Like a bunch of you guys did. One of the things we would have talked about in physics is the idea of like something that goes up and down and up and down. This is a sine graph. We're going to focus on this over the course of the unit. We can actually kind of graph our Earth's progress around the sun using a sine graph. And you can kind of say that like right here is kind of like the baseline. This could be summer, and then it becomes winter, and then it becomes summer again, and then it becomes winter. And we're kind of at the point right now where the days are starting to get longer and longer, right? We need to have our time change again. We're kind of at the point of the year where it's probably right about here again, where we're kind of halfway between summer and winter. Does that make sense at all? Oh, and I guess the point I wanted to make is that circles actually have a lot to do with sine and cosine and how you can make graphs that look like this. So that's why I throw that as my beginning slide. Hopefully it'll make more sense as we go through our unit. Okay, here's what we learned last year. So I actually stole this directly from our slides last year. If we were to take an angle and try to plot it directly onto like a coordinate grid, here's the terminology we use. This angle line right here is called the terminal arm, and this one's called the initial arm. And it always has to go right through the center. Like the vertex has to go through the origin. Is that familiar? I already kind of drew this. We would then draw a bit of like a right angle triangle right here, and this would be our angle. In terms of other terminology we learned, everything can make an acute angle. Do you guys know what acute angles are again? Less than 90, yeah, small angles, less than 90-degree angles. For example, see how right here, when I put the arm, the terminal arm in the second quadrant, it ends up making it so that this angle right here is like an obtuse angle. From the start, right here, the terminal or the initial arm to the terminal arm is hopefully it's clear that it's more than 100 degrees, more than 90 degrees. Well, we always draw a reference angle then back down to the x-axis, and this angle right here would be called a reference angle. Does that make sense? If this is 115 degrees, then what is this little reference angle in here going to be? Exactly, yeah. It would add up to 180, so 115 and 65 would add up to 180. And so regardless of where you plot a triangle or plot an angle, you should be able to find a small triangle in there. It's always made against the x-axis. So if you go, like, say, down in this quadrant right here, the entire angle right here, I don't know exactly what its measure is, but I know it's more than 180. Does that make sense? It has to be more than 180 because this would be where 180 lies. So let's say that this is like, say, 210 degrees. If it's 210 degrees as the entire angle, then this little blue angle right here would be 30. And we call it a reference angle. Does that make sense? Or that's familiar? Why did I have this in here? Oh, yeah. I remember why. I was at a teacher's convention math seminar, and I learned something that I had never heard before. And so I found a picture of it and added it into my notes. You guys know how we start with like this as being 0 degrees right here? And then we make this be 90 degrees, and this is 180.
Please excuse the interruption. Any grade 8 needing retake, please go to the meeting room. Any grade 8 needing retake, please go to the meeting room.
I actually learned at a seminar why we start with 0 right here on this corner. Because it might make intuitive sense to make 0 be up, like straight up. Because like say on a map, we often make north go up, right? And north could be 0. Yeah.
There's a few different methods actually.
There are, yeah. Because we talked about navigator versus Cartesian system. Yeah. So this system right here was developed mostly because the idea was that, like, you know how the sun starts in the east? I mean, technically the sun doesn't actually start there. We actually rotate. But does it make sense that the sun starts in the east and sets in the west? Well, using that system, if this is north, and this is east, and this is west, and this is south, they started to 0 degrees in the east, because what's happening is the sun is starting in the east and setting on the other side in the west. That makes sense? So that was why they chose, for at least this particular system, to start 0 degrees off on the right-hand side, as opposed to a different system. I don't remember which one it was.
I think that
Navigator?
Navigator.
Starts with 0 at the top. Yeah.
That's what they use in like ships.
Yes. Yeah. So, does that make sense though, that idea? So technically this right here should be actually like shifted 90 degrees so that this is like your y-axis right here, and this is your x-axis. It really is a lot of printing going on, isn't there? Alright. You guys know about the quadrants as well. I feel like I've talked about that already. More pictures about reference angles, but hopefully that's something you guys are fairly familiar with still. Not getting any major arguments. Okay, I think this slide right here, I just wanted to show a few different possibilities. Right here, this is an angle that's going in the positive direction. So this might be like, say, plus 30 degrees. If you go backwards around the circle, did I talk with you guys about that last year? Okay, this would be considered a negative answer. As soon as you start going the other way around the circle, this would be like, say, negative 110 degrees. The reason it's negative is because we're going to go clockwise rather than counterclockwise. So if you like use the example of the sun is supposed to go from the east overhead and go to the west. Well, here this angle has been drawn as though the sun starts in the east and goes like below the surface of the earth. That's not exactly how that works. So the point I want to make here is if you go backwards, we use negative angles. This one right here, the point I want to make is that you can go around the circle more than once. Here I've gone all the way around the circle once, and then I went just a little bit further. This might be something like 390 degrees. 390 meaning that we went all the way around the circle 360, and then we kept going a little bit further. Does that make sense? So you can have angles then that are negative angles, positive angles. So when we eventually talk about the domain of angles, you can actually use anything you want. You can use negative for angles, you can use positives for angles, you can use very large numbers for angles. Any of you guys skiers or snowboarders? If I talk about a 1080, what does that mean in snowboarding lingo?
It's like 360s.
Yeah, 360s. Yeah, the same sort of thing works in our math class here. Is if we go around the circle 3 full times, that's a 1080. It is a lot. Yeah. Okay, here's something new then. So this is probably where the main stuff needs to start. The idea is going to be that You're really distracted today, I don't know you guys. Can you close that door once you're done with that? Where should I start with this? I lost my train of thought. Okay, when you guys are little and you're in grade, I don't know, 3, and they teach you about angles for the first time, I think we teach you guys how to measure angles based on 360 degrees because that's just something that kids intuitively can pick up on. Like everyone kind of understands that 180 is half a circle and 90 is like this. Does that make sense? Truthfully though, degrees is actually not the original measure of how to measure angles that mathematicians had. The original measure is something called radians. Do you guys know in your calculator where the radians toggle button is? I should probably start with that. If you go mode and you go down, my calculator is already set to be in something called radians. Yours might be in degrees. So probably the first thing I need to show you is that you need to know how to toggle between these two buttons because these are the two main ways of measuring angles. One is degrees and one is radians. Radians is probably the oldest method that they have of measuring an angle. And here's the definition of a radian. It occurs when you have a circle, and what ends up happening is this length right here is a radius from like here to the edge of the circle. This length right here is also a radius from here to the edge of the circle. And the distance around the edge of the circle, we normally call that an arc. Well, when the arc length is the exact same as the actual radius itself, this has been defined as 1 radian. And that was probably the most original method of measuring things because if you think back to like, I don't know, thousands of years BC or hundreds of years BC, like I think back to like, I don't know, Archimedes and Ptolemy and some of those other famous names you've heard of, they didn't have protractors and compasses and rulers to measure with. Does that make sense? And so the way they measured an angle was based on here's how wide the circle is, and here's how big the edge of the circle is. If it's the same, that's called 1 radian. No, it's just a warning of that. It's okay.
I actually appreciate that. You'll be distraction. What's that?
Thanks. Okay, let me just do a side activity here. I feel like I'm off my topic, so let me restart again. Let's say that we had like a circle on a grid like this, and I started right here, and I asked for you to try to estimate this angle right here. Could you guys estimate approximately what that angle is in degrees? Sure. 30 something seems like a reasonable estimate in degrees. Okay. If I were to draw another one here and say that we started here and we ended right about there.
Any grade 9s needing to do retakes?
Okay.
Grade 9s who need to do retakes, please go to the meeting room.
Anyone want to take a stab at about how big this angle here would be?
210.
I need to go bigger than that. This is 180, and that's 270. Yeah, 260, 250 maybe. I mean, not that 210 is not completely unreasonable, but I'd say probably 210 should have been right about there. I would say that one of the reasons we teach you guys degrees as a way of measuring angles when you're in like elementary, junior high is that you're pretty good at it. It's fairly intuitive and it's easy to figure out. The problem with measuring radians is that you have to then figure out how much of the radius is there around the edge of the circle. So if I want to do the exact same sort of activity, only doing it with using radians, you have to imagine that this right here is a radian. I like to think of it in my mind as like the perfect slice of pizza. So I think I actually have that as my next picture here, where like here's a pizza, and like if you went to Costco and you bought like one of their really big slices of pizza, like a radian's worth of pizza is where however far it is around the edge is the same distance as it is from the center. That is known as a radian. Out of curiosity, any guesses as to how many slices of this perfect slice of pizza you could get in a pizza?
6.
It's roughly about 6. I actually have a slide coming up here that talks about how that works. 1 radian is about 57 degrees, just so you know. And so 57 degrees means you can fit about 6 of them into a pizza. It's actually more than 6 though. I want to show you this slide here. You can find the next one. So imagine this is a slice of pizza. Here's 1, 2, 3, 4, 5, 6, and you're left with just a little sliver left over. Like this is the person who kind of gets gypped and gets like a leftover bit. They actually determined that this last little bit here is 0.28. So what that means is that there are 6.28 radians in a circle. Well, 6.28 is actually based on a different number. And I'm going to flip back to the previous slide again here. Okay. Do you guys remember the formula for circumference of a circle?
Is that 3.14?
Times 2. Yeah. 6.28 is actually 2 times pi. Here's the reason why. The circumference of a circle is 2 pi r. That's hopefully a formula you guys have heard before. Circumference is equal to 2 pi r. Well, based on the way that radians work is that the number of radians you have is the area around the edge of the circle, or circumference around the edge of the circle, divided by whatever the actual radius is. What ends up happening is radius actually cancels out, and it means that 2 pi is how many slices of pizza there are in a circle. Well, 2 pi is roughly 6.28. Here's what makes radians so frustrating then. We don't work with decimal numbers. We're going to talk about things in relationship to how many pi there are. And so it takes a while to retrain your brain to stop thinking about things in degrees and start thinking about them in terms of how many pi there's going to be. Awkward, tricky. So I want to go back to just drawing some pictures here again. all the way around the circle is 2 pi worth of like radians. Basically just over 6 radians. 6 of those perfect slices of pi. Well, if all the way around the circle is 2 pi, then what would halfway around the circle be? Pi, yeah. Technically, you can fit 3.14 perfect slices of pi into this. And if you look at one of the pictures I have, for example, here's like the circle. Just going to try to draw a grid there. You can fit 1, 2, 3, and this little sliver right here would have been 0.14. So you can fit exactly pi pieces of pie in there. Poor choice of word. Okay. What would this right here be equivalent to then? Good. We write that as pi over 2 typically. So this is like 0. And then as you go around the circle, this is half of pi, which is like 1.5 or something like that. Then this is exactly pi, 3.14. And then over here, it's 1.5 pi. We typically write it like this, 3 pi divided by 2. It's like 3 over 2 is 1/2. And then all the rest of the way around the circle is 2 pi. Based on this, it leads to some conversions I need you guys to know. What would this have been in degrees? Good. Pi over 2 is equivalent to 90. Pi is equivalent to 180. 3 pi over 2 is equivalent to 270. And 2 pi is equivalent to 360. My goal over the course of this first week or so is to help you retrain your mind to be able to think not only in degrees, because degrees is useful, but also to be able to think in what's called the radian unit of measurement. And it's challenging because everything involves pi, like the symbol pi. Okay? And so sometimes you may just want to draw this out at first to get an idea of how it works. Does that make sense so far? Okay. Let's try an example here. Well, I guess I actually even have this one here you can look at. Based on how this works then, 360, a whole circle, is equal to 2 pi, which is basically 6.28 radians. 180 is pi. 90 is pi over 2. Using that same logic then, if I keep cutting things in half, 45 degrees, like this right here, would be 45 degrees. That's going to be quarter of pi. Or in terms of how many radians that is, if you want a decimal number, 3.14 divided by 4 should be just under 1 radian. Because I think pi over 4 should be like 0.8 or 0.9 maybe. I don't know my calculator nearby. I'm going to do pi divided by 4 in the calculator. Okay, so 0.8 is pretty close then. Is this right here the perfect slice of pizza? I'd say no, not quite. The perfect slice of pizza might be just a little bit bigger. That would actually be 1 radian right about here. It's just under 60 degrees is the perfect piece of pizza. Okay, so here's our first activity then. About how big is 30 degrees? Well, I would say if I was using my hands, 30 degrees is like maybe that big. And I'd say most kids are pretty good at being able to say, I know about what 30 degrees is. My question now for you is, can we convert this into radian units? I'm a big believer, in all my classes, science especially, let's use a ratio system. So I like doing it like this. Start with 30 degrees and multiply by a ratio. We just need to know a common ratio we can use. And I think this is probably the most appropriate one to say. I want to throw a degrees symbol on the bottom so that the degree symbol cancels. And I want to have like radians on the top. I'll just write it as rad. How big is a circle? Well, either 360 if you're talking about degrees, or 2 pi, which is like 6.28. These things are equivalent to each other. 2 pi is the same thing as 260, so this is another ratio that works. So the degrees symbol will cancel. What we need you guys to do is take your calculator, take 30 times by 2 pi and divide by 360. So if I take 30 and times by 2 pi and divide by 360, how many radians is this? Before you even press enter, is it going to be a full radian? This little bitty slice of pie? I would say it might be less than half a radian, maybe. Okay, about half a radian. Does that make sense? So if a full radian is like that perfect slice of pizza, and I'm just, like in my mind, I'm thinking Costco. You guys know what I'm talking about? Like those big slices I sell there? No. This is about half of that. So here's the problem though. Although writing it is 0.52, I mean, that is a valid way of writing it. That is a rounded number. And we really prefer not to write it as a rounded number because at some point we have to, like, it's going to be slightly off by rounding. Does that make sense? So the typical way of writing this then is by not using pi. Pi is ultimately the problem. Pi is an irrational number. So times everything and divide everything that's not the number pi. So I'm going to do this again. I'm going to do 30. I'm going to times by 2, but I won't times by pi. And I'm going to divide by 360. And then I'm going to go math, fraction. And I get 1/6. The better answer for this is 1/6 of pi. Now, I'll try checking them both. You know how I had 0.523 like that? If I take 1/6 and I time 1/6 by pi, you should get that number again. But this is the more preferred method of writing it. Because, yeah, that's a good reason too. So that's my goal this first week here, is to help retrain your minds to learn everything you've learned from grades 1 through grade 11, but working with pi units instead. It's like a completely different way of looking at things. Let me try the next one. Take 120 times by 2 pi, divide by 360. Oh, by the way, quick note. When, you know how I wrote RAD right here for radians? Typically people don't do that. Typically if you see pi, pi implies that it's in radians for units. So we don't actually write RAD for radians afterwards. You can, but we typically just choose not to. Okay, so if I'm trying this one here, take 120 times by 2, don't times by pi, and divide by 360. Make that a fraction. This would be 2/3 of pi. I'd like to sketch where about that would be then. Do you guys remember drawing like a circle like this? This would be 0. All the way over here would have been considered pi, because pi is 180. 2/3 of pi then would be like roughly, this is the first third of pi, this is the second third, this is the third third. So 2/3 of pi would be from here to there. That's 2/3 of pi. Does that look like it could be about 120 degrees? Hopefully you'd agree and say, yeah, 120. I mean, it's more than 90. Okay. You can even do it for like more challenging numbers. You can do 153 times by 2. Don't times by pi. And then divide by 360. Make it into a fraction. And so you could have, this guy right here is 17/20ths of pi. Well, if I was drawing 17/20ths, is that greater than 1 or less than 1? Less than 1. 1 pi is directly over here at 180. So if this is 0, and this is half of pi, and this is like a full pi, 17/20ths means you have to imagine that you broke this thing up into 20 pieces. So that'd be like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Imagine I did that properly, right? You'd count over and you'd say 17 of them would be right about here. That's 17/20ths. And then that angle right there is 17/20ths of pi. Or in degrees, you guys would recognize this as being 153 degrees.
So what about when they start getting into the third and fourth?
Okay, I've got some of those coming up in a bit. Let's do one right here anyways, since you asked. Let's do another one here. So let's pick something that's well over 180 degrees. So let's pick 259 degrees. Based on 259 degrees, I should be able to guess about where that's going to land. So if this is 0 degrees, and that's 90, and that's 180, and that's 270, 259 should be right about there. That makes sense? Okay, so now let's do the exact same thing. 259 times by 2. I'm going to times by pi just to show you something tricky here. Let's say that you accidentally times by pi and you get this 4.52. That's how many perfect slices of pie there would be. But if that doesn't help you nearly as much, what you could do is redivide this number by pi, and then you should be able to make a fraction out of it. So apparently this number right here is 259 180ths of pi. Do you see how this fraction right here is greater than 1? So I guess what you'd have to do is right here you'd have to divide this up into 180 little sections. That would be ridiculous. Then you'd have to divide this up also into 180 different sections. And then you'd start counting here from 0. And all the way up to here would be 180 of them. And somewhere around here, you'd get up to your 259. So we wouldn't actually do it for a number like this, obviously, right? But does that make sense? Okay, let's try the other half of the question then. So this one's now about, what if I give you something in radians? Can you convert it into degrees? So the first one is 5.27 radians. Anyone want to take a hazard as a guess as to how many degrees you expect that to be? Okay, well, I'm just going to start drawing it out here. This is probably about 1 radian. That's about a perfect piece of pie. And then somewhere around here is about that 2nd radian. The 3rd radian is just right above there, so that's 3 radians. 4 radians probably comes to about here. 5 radians should be about here. So I'm going to say 5.27 radians should be somewhere in this quadrant here. So you said more than 270? So I'm going to hazard a guess. I'm going to say roughly about 300 degrees. That's my guess. What's that? You already figured it out? Okay, well, if you can figure it out, here's what you do then. Take 527, and rather than multiply by 2 pi and divide by 360, multiply by 360 and divide by 2 pi. Because essentially this thing right here is in radians, and this one right here is in radians, and that cancels. The only thing I got to make sure I'm really clear on, when you divide by that 2 pi, put it in brackets. Because otherwise your calculator is going to think that you're taking this number timesing by 360. It'll think you're dividing by 2, but it'll think you're timesing by pi. So do this, 5.27 times by 360 divided by bracket 2 pi. And yeah, basically it was 302 degrees. Does that work? So let me try the other ones here. I do want to graph all of these just to help retrain your minds to thinking in this radian unit of measurement. So before I do anything, I want to try to figure out where about 5 pi over 6 should lie. So first I'm going to draw a grid. This is 0. That is half of pi, and this is a full pi. 5/6 of pi would look like this. Here's 1/6, 2/6, 3/6, 4/6, 5/6, and all the way over here would be 6/6. That would be the full pi. So 5/6 of pi would be like this section right here. Does that make sense? So roughly guesstimating an angle, I'd say, well, it's definitely more than 90. A little bit less than 180. 160-ish, yeah. That's my guess. So now let's write it out here. You're going to do 5,
Any grade
6
10s needing
pi
to have retakes? Grade
multiplied by
10s,
360.
please come
divided
to
by
the
2
meeting
pi.
room for retakes.
One of the nifty things about doing this is you see how this pi right here is going to cancel with that pi right there. All we have to do then is take 5 times 360. We have to divide by 6, and we also have to divide by 2. And it's 150. So 160 is pretty close though. One last one, and then maybe we'll take a quick break here. Is anybody needing retakes today, by the way? Okay, let's do this last one, then we'll take a break. So, I want to draw where about 3/8 of pi is. Just going to get rid of all this so I have more room. So 3/8 of pi, if this is 0 and this is half of pi, 3/8 is less than half. Does that make sense? Because 4/8 would be half. So I'm going to break it up into like 1, 2, 3, 4. Technically, I could keep going and go 5, 6, 7, 8. So there's all my 8ths of pi. This pi should be over here. 3/8 would be 1, 2, 3. So 3/8 of pi should be this. That looks like it's just over that perfect slice of pie. It's not quite, but maybe a little bit bigger than that. So to do the math, go 3 pi over 8. That's how many radians there is. So times by 360 degrees to get a degree symbol up here, and put the 2 pi on the bottom. Because what happens then is this pi and this pi cancel, and we just have to do 3 times 360 divided by 16, I guess. 3 times 360 divided by 16 gives you 67.5 degrees. I think that's about right. This looks like it could be about 67.5 degrees. Does anyone remember exactly how much a radian was again? Yeah, it's about 57 degrees, give or take. So this is slightly bigger than that perfect piece of pizza. Okay, that's probably a good place just to take a pause right now. Just a quick summary then. Most of my goal this first week is to reteach you trigonometry stuff that you've learned, but now we're going to do it all in a different unit. Rather than in degrees, we're going to do it all in versions of pi. And that's it's a lot trickier to try to think of, because in my mind, I know what 120 degrees looks like. But if I ask you for 5/7 of pi, can you think of where 5/7 of pi would be? It's a little more challenging. I'll just do that and end it here. Where would 5/7 of pi end up being at? Well, here's 0. Here's half of pi. There's pi. I have to convert this into sevenths. I guess that would be like, say, 1, 2, 3, 4, 5, 6. And that one's 7 right there. So 5/7 would be right about here. So I would guess 5/7 of pi to be 100 and something degrees. Does that make sense so far? Right. Go take 5 when you come back. I've still got more though. Sorry. First lessons are always really long. Okay. I think I'm at the point of the lesson now where almost everything else is. I've got a bunch of practice old diploma questions as some of my next slides. Before that, though, I need to show you the first trigonometry formula. Do you guys have your formula sheets or have one nearby? We haven't hardly even used them. This is the unit that more or less everything is saved for. There are a whole bunch of formulas that we can use in trigonometry. So I want to talk about one of the very first ones. It looks like this, hopefully. It's that an angle is equal to an A divided by an R. You guys have that formula on the top of the sheet there? Okay. This first formula then is the definition of what a radian is. An angle in radians is however much the arc length is divided by its radius. Okay. The one thing about this formula though is that this right here has to be in radians for it to work. Very, very rarely from now on are we actually working in degrees. It'll happen once in a while, but almost all the rest of the time we work in radians. So let me try some examples with you. This is something like that would be a very basic level diploma question, and I have a bunch afterwards to show you. Let's try to find the angle right here. That's what you do. Yeah, to find the angle, it would be 45 divided by 20 because that's your arc length, that's your radius. Is it a radian? Well, actually, it's more than a radian. It's like 2.25 radians. In terms of writing this then, we could write it like this, 2.25 radians. Sometimes we write it in terms of pi. but we really can't convert this one into terms of pi, so we're kind of stuck there. We'd say you basically have 2 1/4 radians. We can go backwards and find an arc length. So we could try to find like this distance around the edge of the circle here, using that same formula. An angle is equal to an arc length over a radius. Here's the problem though. This 53 degrees, I don't do this. Don't plug in 53 equals the arc length divided by 16. That's not right, because it has to be in radians. So the first thing we have to do is take 53 degrees and times by 2 pi divided by 360. Now, normally I might say leave pi out of the equation because you want to have it like as a fraction. But to be honest, in this one right here, we can probably work with a decimal number so long as we never ever round it. So, yeah, like it should be just less than a radian, right? So 53 times by 2 pi divided by 360. Yeah, so 0.92 ... So if you make it 0.9250 equals the arc length over 16, if you times up by 16, that'll give you your arc length. Yeah. Now the diploma would ask you to round it at some point, so it probably would be 14.8 is how they'd ask you to round it. That's how many centimeters it would be around this edge right here. If it was exactly 16 and 16, it would be 1 radian. So since it's 16 and 14.8, it's slightly under a radian. Does that work? Okay, let's try some diploma questions then. So these are off of old diploma tests. So here's the first scenario. Imagine that you're in like a baseball diamond of some kind, and the baseball diamond has a central angle of 97 degrees. And you get to know the radius of this. It's 30 meters. So we want to find the total length of the sidewalk. So first thing I might suggest then is we have this new formula. To find an angle, it's equal to the arc over the radius. We actually have the radius. The radius is 30 meters. But what we don't have is an angle we can work with. But we can convert. We could write it as 97 degrees multiplied by 2 pi over 360. I can convert this angle from degrees into radians. And when I'm done, I'll times up by the 30, and that'll give me my arc length around this unknown edge. So 97 times by 2 pi divided by 360. So I got about 1.69 radians. Times that by 30. I have an arc length of 50.8 meters. Anybody else get that? Okay, that's not the right answer. No. It's actually not about that. It's about this. It's the total length of the sidewalk.
So then you have to add the...
Yeah, because basically to this 50, you have to add an extra 30 for this edge and an extra 30 for this edge. So, does that make it 60 and 50 would be 110.8 meters. And then now, because you have to round to the nearest meter, you're going to have to make it 111 meters. Does that make sense? All right. Any questions on that? We're good. Okay. Like I said, here's a whole bunch of old diploma questions. So here's one about a satellite orbiting the Earth, and we want to try to figure out the height of the satellite above the surface of the Earth, basically. Can you guys see on your copy? There's an angle hidden in here at 55 degrees. Is that seeable for yours?
Yeah. You really look at it.
Okay, 55 degrees is your angle. Ultimately, what we're looking for then is the height of the satellite above the Earth. We're looking for this distance right here. We can't really do all of that, but what we can do is we can figure out the height from here to the center of the Earth. And you see how it says the radius of the Earth is 5,000? we'll subtract a 5,000. So work with this slice of pi right here. It's just under a radian. So our formula is theta is equal to an arc length over a radius. The only difference here is that we actually have the arc this time. So this would be 55 times 360 under 2 pi. The arc length is the 8952, but what we don't know is the radius. So how do I get the radius by itself then? Yeah, switch those guys around there. So here's how I do it in my calculator. I'm going to do 55 times by 2 pi divided by 360. So just under a radian. And then this r and that number need to flip around. So I'm going to take your 8952 and I'm going to divide by that number. And that means that your radius should be 932566. However, that is the whole radius from the center of Earth all the way to the actual plane itself, or satellite itself. So subtract your 5,000. Yeah. And I believe that one was C. Does that make sense? Okay, before I do my next question, I just need to remind you of a concept that I don't know that I used this word last year or not. So it's called a coterminal angle. Did I talk about this last year with you guys at all? I don't think so. I don't think I did it with grade 11s. I probably should. Basically, the idea behind coterminal is that the angle remains the same, but we have a different way of writing it. Here's an example. Right here, this is actually not pi. It's pi over 2. I have a typo there. This is half of pi. If I go forward around the circle, I need half of pi. Or if I go backwards around the circle, I would need 1.5 pi. Does that make sense? Either way, it's the same angle. The angle is still this. It's just one is the short way around the circle, and one is the long way around the circle. Here's another example of coterminal. Here's an angle that's 130 degrees. Here is the same angle of 130 degrees, but I went around the circle an extra time, and so this is 490. Well, 130 and 490 are coterminal because they end up being in the same direction either way. If you were to spin around in circles 5 times and then go your 130 degrees, you're still facing the same way as the person who just went 130 degrees. Does that make sense though, that they're the same ultimately as each other? So that's a word you might come across. So here's another example then. Which of the following is not coterminal to 150? So like 3 of these things mean the exact same thing, one of them doesn't. So I'm just going to sketch out where about 150 degrees would be. 150 degrees would be roughly right about there. So let's test out negative 930. How can I kind of figure out whether negative 930 means the same thing as 150? I do this myself. I take negative 930 and I add 360. So I go around the circle once. And I add 360. I go around the circle again. Then I add 360 another time. And do you guys see how I ended up with 150? Well, all that means is that 360, 360, 360. If I went around the circle 3 more times, these two things are the same as each other. So yes, this one is coterminal to 150. It just means that you've gone backwards around the circle 3 times, that's all. The next one I need to write out a line of work for, 17 pi over 6. What I could do is I could then use my 360 over 2 pi ratio and try to find out what that is in degrees. So 17 times by 360 divided by 6 divided by 2 gives me 510 degrees. 510 degrees means you've gone all the way around the circle a little bit too far. Like you've gone all the way around once at the very least. So if I subtract 360 from that, I got 150. So this one is also coterminal. Does that make sense? Let's try 23. 3 pi over 6. I'll do the same thing. I'll do the 360 divided by 2 pi. So 23 times 360 divided by 6 divided by 2. I get 690. So then to figure out whether 690 is in the exact same quadrant as 150, I'll subtract 360. Gives me 330. If I subtract another 360, it ends up being minus 30. That's not in the same spot, is it? So that one's the answer where it's not. I just want to prove the other one. Negative 3.67. You know what I could have done is I could take 150. I could times by 2 pi divided by 360. Times by 2 pi divided by 360. That would give me 2.617 radians, which is going forward around the circle. If I wanted to go backwards around the circle, I could minus. Now, you know how last time I was minusing 360s? Well, I'm working in radians now, so I should really minus 2 pi. And there's that same number again. That gave me a 2.617 radians. I minused 2 pi, and it's the same thing as going backwards, 3.67 radians. So if you go forward roughly 2 slices of perfect pi, it's the same thing as going backwards roughly 4 slices of perfect pi. Does that work? Okay, another concept that I want to talk about is called general form. How do I put this here? I'm just going to draw out an angle here. Let's say this angle right here is 30 degrees. In theory, this angle could be written as 30 degrees. It could be written as 390 degrees, because I'm going around the circle an extra 360. I need my calculator for the next one. 390. Oops.
Any grade 12s that are wanting retakes, please go to the meeting room. Any grade 12s wanting retakes, please go to the meeting room.
You could have written this as 750. You could even subtract and go 30 and subtract 360. And you could get negative 330 degrees, which means you're going all the way backwards around the circle 330. All of these angles are considered coterminal. They're all equivalent to each other. So we've developed a way to kind of write out this angle in what's called general form. For the angle I have right here, here's how I would have written it. I would have written it like this. 30 degrees is my base angle, and I could either add or subtract a full circle an unknown number of times. This is known as general form. See, 30 is my base angle. I could have added 360 and got 390, which is going around the circle again. I could have added another 360 and gotten 750. I could keep doing that for forever if I really want to, just keep spinning around in circles. Or I could spin around in circles backwards. So this is called a general form. So I want to try doing that for 892. 892 then would mean that you've gone around the circle clearly more than once. So I'd like to try to figure out where does 892 kind of lie. So I would take my calculator and I'd go 892. I'm going to minus 360. Still too much. Minus another 360. Not really. It's equivalent to 172, which would be roughly right about here. Well, my general solution then means take 172, and either you could add or subtract a full circle's worth an unknown number of times. This is known as a general solution. So if you added 360 and added 360, you would get back to 892. How does it change if it's 5 pi over 2? I just want to talk about how pi worked again. You start at 0. This is 1/2 of pi. This is a full pi. This would be 3/2 of pi. This would be 4 halves of pi. This right here would be 5 halves of pi. It means you've gone around the circle a full time and then you went a little bit further. 5 halves of pi ends up right here. Does that make sense how I kind of cut them off into halves? So half, a full, 1.5, 2. This is 2.5 pi going all the way around the circle and ending up on the y-axis right there. So to write this in general format, I would say, well, half of pi is as low as you get. Now, rather than adding 360 to it, though, the idea is what I should add and subtract. Perfect. Yeah, you're going to add and subtract 2 pi. N is for an unknown number of times. Because we don't know whether we're going to go around the circle twice or 5 times. We could even go backwards around the circle and find negative values. Does that make sense? Okay. I think that was my last slide. Okay, so summary of what we learned today. This is a very frustrating lesson for me to teach. I don't know if it's frustrating for you to learn, because we're doing all this stuff in radians. You might ask yourself, why? Well, isn't degrees just a simpler way of working with things? And I'd agree. I'd say from grades 1 through 11, it makes a lot of sense to work with degrees, because you're pretty good in your mind, I think, at recognizing degrees. But I have 2 main reasons why I need you to know radians. 3 main reasons why. First main reason is they're going to ask you it on a diploma, so you just better know it. But if you actually want to have some rational reasons otherwise, here's the 2. Radians are probably a better method of measuring things because it's not based on this arbitrary choice of making a circle being 360. To some degree, pun intended, I guess. Why did we choose a circle to be 360 degrees? Is there any logic behind that? Why couldn't a circle have been 100 degrees? And then this right here would be 25, and this would be 50, and that would be 75, and all the way around 100. Why would that not make more sense? We've made 360 degrees an arbitrary number. I think the reason why actually is because the Earth goes around the sun in 365 days, and 360 is kind of close to that. But I mean, isn't that bad logic to base all of your math systems off of? You know what I mean? Like, that's just, why would we do that? Also, from what I understand, radians is actually an older method of measuring things because it's based purely off of, like, if this is how far I can go in one direction, and this is how far I can go in the other direction based on a radius, then a radian is like that same length around the end of the circle. It's that perfect slice of pie. Now, I think that's fairly logical as like a math reasoning, but it's hard. It's challenging. Does that make sense?
So I'm going to do that. I'm going to go home and measure radians.
Measure everything in radians, yeah. The other reason why I think this is purposeful is that there is one formula we've learned so far, the formula that an angle is equal to an arc length over a radius. This is a very useful formula, but the only problem is that for it to work, it has to be measured in radians, not in degrees. And I mean, there were 2 questions there we did. I mean, maybe you don't care about baseball fields or orbiting satellites, but I mean, it is something that is useful. So that's my goal for the day. Can you guys start to visualize things not in degrees, but in radians? So in terms of fractions of pi. The better you get at that, the easier this unit will be. Any questions? All right. You guys can probably do basically question 1 on your assignments, and that's about as far as you're
Any
going to get.
staff members who still have not had your picture taken, please go down to the meeting room.
Perfect. Thank you.